Hello viewers and Dr. B.R. Ambedkar Open University students. Today we are going to discuss about the ethers and epoxides. So ethers are the organic compounds which are composed with the two alkyl groups attached with the oxygen. Generally the ethers are called as the derivatives of water because in the water H2O the to the oxygen either side the two hydrogens are going to attach. So in the place of hydrogens in the ethers the alkyl groups are attached to the oxygen. So that is why it is called as the derivatives of the water molecule. So here the ethers are two types based on the alkyl groups attached with the oxygen. So based on that alkyl groups it is divided into two types like symmetrical ethers and unsymmetrical ethers. The general formula for the ethers is ROR. Here R may be the alkyl group or aryl group. Alkyl groups mean any methyl, ethyl, propyl, isopropyl, these groups. Aryl groups means aromatic groups like benzene and naphthalene. So here the symmetrical ether and unsymmetrical ether means where the two alkyl groups are same, those are called as the symmetrical ethers, and where the two alkyl groups are different, then it is called as the unsymmetrical ethers. Here some examples are given, like here diethyl ether, to this oxygen two ethyl groups are going to attach here. So two ethyl groups are same, so it is called the symmetrical ether. And in the next example it is methyl N propyl ether. So to the oxygen the both side the different alkyl groups are going to attach. So it is called the unsymmetrical ether, means here one side methyl group is there, another side propyl group is there. So it is called unsymmetrical ethers. So the nomenclature of the ethers. Ethers are given the two types of nomenclatures. One is the IUPAC nomenclature and the common nomenclature. Generally in the IUPAC nomenclature the ethers are considered as the alkoxy alkanes, and the common nomenclature the ethers are called as the dialkyl ether, means here the alkyl group is given the name and finally it is mentioned the ether name, but in the IUPAC nomenclature it is considered as the alkoxy alkane. So here the two different types of ethers are given. Here if you see here the first one is a dimethyl, means here the two methyl groups are attached with the oxygen. So in the common nomenclature name is a dimethyl ether, and IUPAC nomenclature it is called methoxymethane. And in the second example here the means here the to the oxygen two different groups are going to attach here. So it is unsymmetrical ether. On one side it is methyl group, another side it is ethyl group. So the common nomenclature it will be the ethyl methyl ether, and IUPAC nomenclature is a methoxyethane. Next example is one side is methyl group is there, another side is propyl group is there. So the common nomenclature may be the methyl propyl ether, and IUPAC nomenclature is a methoxypropane. Here the how the IUPAC nomenclature and common nomenclature is given to the ethers. So here one rule is there for the common nomenclature. If the two different alkyl groups are attached, then we should follow the alphabetical order. For example here in the unsymmetrical ether, here the ethyl group and on the left side it is methyl group is there. So in the alphabetical order the E comes first, so the ethyl, then the M comes second. So ethyl, methyl and ether. And in the IUPAC nomenclature, while you are giving the nomenclature to the ethers, you should mention the, means you should combine the oxy group with the lowest, means the smallest alkyl group. In that case here for this example here the ethyl group is there and methyl group is there. So among the ethyl and methyl, the methyl group is the smallest group than the ethyl group. So the oxy group should be attached with the methyl. So it is called the methoxyethane. And in the next example it is methyl and propane. So propane group is the largest group where the methyl group is the smallest group. So, in the IUPAC nomenclature, it is combined with the oxy with methyl. So, it is becomes methoxypropane. So, this is nomenclature of the ethers. Then the preparation of ethers. So, generally the ethers are prepared by various methods, but frequently used and very useful method for the preparation of ethers is a Williamson synthesis. So, here the Williamson synthesis involves the reaction of the alkyl halide with sodium alkoxide. So, when the sodium alkoxide ion is treated with the alkyl halides, then it gives ethers. So, here the both symmetrical ethers and unsymmetrical ethers will be prepared by the Williamson synthesis. So, in the given example here, for example, here sodium alkoxide which is treated with the alkyl halide and it is giving the ether moiety, where the if you take in place of R group, if you take the alkyl group, that is the ethyl group. So, when we treated with the sodium ethoxide with methyl bromide, then it becomes a methyl ethyl ether, and sodium bromide is a byproduct here. In the same way, if you take the ethyl bromide and when it is treated with the sodium ethoxide, then it becomes diethyl ether, symmetrical ether will be going to form here. And here one condition is there, when we take the bulkier alkyl halides, when we treated with the bulkier alkyl halides with sodium alkoxide ions, then here the two types of reactions will be takes place, where in generally Williamson synthesis the substitution reaction will be takes place, but when we take the bulkier alkyl groups, then the elimination reaction also will be takes place. So, in that case you have to take the substrate as a base, means alkoxide ion should be the bulkier group and the simpler group should be the alkyl halide. For example, here one example is given, like here tertiary butyl bromide, when it is treated with the alkoxide ion. So, here the instead of substitution reaction, it is going to give a elimination product, that is a isobutylene is a major product in this reaction. Here if you in place of here the bromine, if you take the alkoxide ion here, like here sodium tertiary butoxide ion, when it is treated with the ethyl bromide, so we will get the 2-ethoxy 2-methyl propane is a product, where it is a ether product. But if we take this bulkier group with alkyl halide group, so then instead of formation of the ether, we will get this olefin or the alkene is a major product here. So, that is why we should take the bulkier group as the reagent, but not as a substrate. This is a condition in the reaction. Next, preparation of the aromatic ethers. So, when we treated with the sodium phenoxide with alkyl halide, we will get the aromatic ethers. So, in the example here, sodium salt of phenol which is treated with the alkyl halide, so it is giving to alkyl phenoxide group, that is the aromatic ether group. And for example, here the sodium phenoxide is taken and it is treated with the ethyl iodide. So, we are getting the ethoxy phenol, that is the major product of the ether. And when we treated with the phenol with DMS, so we are getting the anisole is a major product here. And here the nerolin preparation. So, when we take the beta naphthol with DMS, dimethyl sulfate, we are getting the nerolin is a major product here. This is the aromatic ether preparation methods. And another important method for the preparation of ether is the ethers will be prepared from the concentrated sulfuric acid. When the alcohols are treated with the concentrated sulfuric acid, we will get the symmetrical or the unsymmetrical ethers. So, in this particular example here, ethyl alcohol, when it is treated with the concentrated sulfuric acid, by losing of water, means dehydration reaction is going to take place here, and it is giving the diethyl ether is a product here. And if you see the mechanism of this reaction, generally this reaction is proceeds through the formation of alkyl carbocation intermediate. So, in the first step, the alcohol which is going to protonated, and it is formation of the protonated alcohol, and then protonated alcohol, by losing of the water molecule, it is giving the ethyl carbocation as a intermediate, and this ethyl carbocation intermediate further reacts with the second mole of ethyl alcohol, and it is going to form a oxonium ion, diethyl oxonium ion, and this oxonium ion further removal of the hydrogen. So, it is going to form a ether product. Next, the general properties of ethers. So, generally the ethers are chemically inert nature, means the ethers are very less reactive compounds. So, because of this inert nature of the ethers are used as solvents in many organic reactions, means these ethers are unresponsive with the acids and bases. So, only in the special conditions the ethers are gives some reactions, but in the normal conditions at room temperature the ethers are chemically inert, means they are not involved in the any chemical reactions, and they not reacts with any acids or the bases or any aluminum chloride or sodium borohydrate reactions. That is why the ethers are called as a chemically inert nature. So, these ethers are used as the solvents in the chemical reactions, because the solvent should not be involved in the reaction. So, in that way the ethers are used as solvents, and these ethers are unable to form the hydrogen bonding with the water molecule. So, these are water insoluble compounds, and the ethers should not forms any intermolecular or intramolecular hydrogen bonding, because there is no free hydrogen which is attached with the oxygen, directly attached with the oxygen. So, they should not form the hydrogen bonding. That is why the molecules, ether molecules are unassociative. So, because of this unassociative nature of the ethers, these are means ethers are having very low boiling point values, means if the any compound which forms the hydrogen bonding, they have the higher boiling point values, but these molecules are not involving in the any intermolecular or intramolecular hydrogen bonding. So, these are unassociative molecules. So, the boiling points will be the very less when you compare with the other compounds. Like here the comparison with the alcohols, when we compare the ethers boiling point with alcohols, very low boiling points will be observed for the ethers. For example, if you observe for the boiling point of the ethyl alcohol and diethyl ether. So, here the diethyl ether, it is having the 25 degrees centigrade boiling point, where the ethanol is having the 78 degrees centigrade boiling point value. Means here the very lot of difference is there in the boiling point of the ethers and ethanol. When you compare with the ethanol, it is having very low boiling point. This is only because of the not formation of the hydrogen bonding, means here the alcohols are able to form the hydrogen bonding, where the ethers are unable to forming the hydrogen bonding. Next, the cleavage by the acids. So, generally here the ethers are chemically inert nature, but when we reacted with the strong acids like hydrogen iodide and hydrogen bromide, here the ether linkage, means CO bond gets cleaved in this particular reaction. And when we take the different types of acids like hydrogen iodide, hydrogen bromide and hydrogen chloride. So, among all these acids, the hydrogen iodide is a strong acid, where the hydrogen chloride is a weak acid. So, here the order of the reacting with ethers is hydrogen iodide will be the more reactive with ethers, then hydrogen bromide, then hydrogen chloride. This is the order of the reactivity with ethers. And in this particular reaction with strong acids, here the ether linkage means here the CO means carbon oxygen bond gets cleaved with strong acids. In this particular example here, when here the ether is taken, dialkyl ether, when we treated with the alkyl halides means alkyl halides here. So, here this bond is going to cleave here, oxygen and alkyl bond is going to cleave, and we are getting the alcohol and alkyl halide as the products here. So, if you take the unsymmetrical ethers, like one is the alkyl group, another is the aryl group. So, here the bond cleavage will be takes place among in between the oxygen and alkyl group, and we are getting the phenol here and alkyl halide here. So, in this way the bond cleavage CO bond cleavage will be taking place. By taking different examples here, if you take the diethyl ether, when we reacted with hydrogen iodide, so we are getting two types of products here, ethyl alcohol and ethyl iodide is the products here. Same thing when we take the diethyl ether and reacted with excess of hydrogen iodide, we are getting only the ethyl iodide is a major product here. Next, reaction with Grignard reagent. So, generally here the ethers, when we take the reaction with Grignard reagent, so here the ethers will be stabilize the Grignard reagent by chelation effect here. So, here in the diethyl ether is taken and Grignard reagent or MgX is a Grignard reagent, and it is very useful reagent in the organic synthesis reactions. So, here the oxygen which is having the two lone pair electrons in the ether molecule. So, the lone pair electron is coordinating with the magnesium, and it is stabilizing the magnesium metal. So, it is very useful solvent, means ether is a very useful solvent to stabilize the Grignard reagent. Preparation of diethyl ether. Diethyl ether will be prepared by the reacting of alcohol with concentrated sulfuric acid. When the alcohols are treated with the concentrated sulfuric acid, by dehydration reaction it gives the diethyl ether. In this particular reaction, here the 2 moles of alcohols are required. The first mole of alcohol is reacted with the concentrated sulfuric acid and it gives a ethyl carbocation. Then the second mole of alcohol is reacted with the ethyl carbocation and it forms the diethyl ether. Next, anisole preparation. So, here the anisole preparation means aromatic ethers. So, here the sodium phenoxide, when it is treated with methyl iodide, so it gives the anisole. Next, the epoxide. So, the epoxide, generally the epoxides are the cyclic ethers. Epoxides are cyclic ethers and heterocyclic compounds, and epoxide means in the ether, normal ether, the oxygen is in free form, but in the epoxides the oxygen is in the cycle form. So, here the 3-membered cycle is having the oxygen as a part of the ring system. So, it is called the epoxide. So, epoxides are very useful reagents, means epoxides are very useful reagents, and these are very useful intermediate for the organic synthesis. So, how to prepare the epoxide? Generally here the epoxide are prepared by treating with the metachloroperbenzoic acid with olefins. When the olefins are treated with MCPBA or metachloroperbenzoic acid, so it gives the epoxide, and chlorobenzoic acid is the byproduct in this particular reaction. So, if you see the mechanism how the epoxides are going to form here, if you see the mechanism, then we will conclude that how the epoxides are going to form. So, in this particular reaction here, metachloroperbenzoic acid is a reagent for the preparation of the epoxide ring. So, here metachloroperbenzoic acid, it is reacting with olefin here, alkene or the olefin. So, in this mechanism this bond means here the OH bond is going to attacks at the olefinic center, then the pi bond in the olefin, it is going to attack on this oxygen, then it leads to formation of a 3-membered cycle here, and which is called the epoxide ring, and this particular compound is removed as a chlorobenzoic acid. In this way we can prepare the epoxide. Then reactions of epoxides. So, generally here the epoxides undergoes the reactions in acid medium and basic medium, and in the acidic medium and in the basic medium epoxides gives the different product, and they follows the different types of mechanisms. Means in the acidic medium and basic medium epoxide ring opening will be takes place. When we take the epoxide in the acidic medium, the mechanism, how the mechanism is established, we can see here. For example, here the epoxide ring is taken and it is treated with the hydrogen bromide. This is the acid, and epoxide ring, the lone pair electrons on the oxygen, it is taking the proton from the hydrogen bromide, and this epoxide ring is going to form a protonated epoxide ring. And the next, the Br minus, where the H plus is going to attach with your oxygen, then the Br minus nucleophile, it is attacks on your epoxide protonated epoxide ring. So, in this particular intermediate, the Br minus, it should not be comes from the front side. So, it will be attack from the back side, because if it comes from the front side attack, because it here the ring is there. So, it faces some steric hindrance. So, bromide ion should not come from the front side. So, it chooses from the back side, because the back side is sterically free. So, and it is very special. So, Br minus ion will be attacks from the back side, and it leads to opening of the epoxide ring, and where it is going to form a bromo alcohol. Next, mechanism in the basic medium. So, generally here in the unsymmetrical ethers, the basic medium attack will be takes place at sterically less crowded position. Here the nucleophile, here methoxide ion, it is going to attack at sterically less crowded carbon in the epoxide ring. So, here the when the base methoxide ion, it will not attack at this carbon, because here the methyl group is there. So, this center is sterically crowded. So, the base should not attack at this carbon. So, it chooses the sterically less crowded carbon center. This center is sterically less crowded. So, it attacks at this sterically less crowded carbon, and it leads to cleavage of this bond, and it leads to epoxide ring opening.